Let's just wait till this starts recording. Okay, I'll start speaking, although the recordings doesn't seem to have started yet. Welcome again, everyone, for this morning's Capstone presentation, our final Capstone presentation for the week. Just as a reminder how this would work, the presentation will last about 15 to 20 minutes. After that, we'll have about 15 or 20 minutes for questions. If you would like to ask the speaker a question, then on the lower bar at the end of the presentation, please click the raise hand icon and I will moderate and call on you so you can ask your question. The next presentation and the final presentation of this week will come from Emerald Liu, and it will be on a history, the development of computers and computer science. So Emerald, if you would please share your presentation with us and take it away.
Thank you, Dr. D. Let me share my screen. 1 second. Hopefully it's up there.
It's coming up right now. Don't forget to use your laser pointer if you need it.
Yes, I will. So hi everyone, I am Emerald Liu, and my Capstone project is on the topic of development of computers and computer science. So computers are pretty amazing. It is truly impressive how they have developed and become so smart nowadays. And in my Capstone project, I explored the significant developments in computers and computer science, both on the hardware and softwares that brought out the amazing technologies we have today. And here are the topics that I am going to introduce in today's presentation: the calculating machines, the analytical engine, Turing machine, the first electronic computer, the internet, artificial intelligence, and quantum computing. So at the very beginning of the civilization, people used to use pebbles and disks to achieve the goal of simple calculations. However, pebbles and disks could not be performed with large numbers, and a better calculating machine was needed, an abacus. This was the first stage of the calculating machines. Abacus were invented during the 13th century, and on an abacus, each vertical sticks represent a digit, and the count of beads on that stick represent the number on that digit. For example, on this graph here, on the top, this would represent a 5, and over here, the 2 beads would represent 2. Abacus is all manual calculations, and each digits need to be changed when carrying digits. Moving on to the second stage of the calculating machines. In 1642, improving upon abacus, Blaise Pascal invented the Pascal line. A calculation can be made by rotating the wheels on the machine. When each digit changes, the gear inside the box would turn, and the next gear linked to the digit, achieving the goal of subtracting and adding numbers. And in 1679, Gottfried Leibniz modified Pascal line and made the Leibniz machine. It achieved an additional feature of multiplication and division by repeating addition and subtraction. The third stage of calculating machine were the analytical engine, designed by Charles Babbage and Ada Lovelace in 1837. So Babbage was inspired by an automatic looming machine that used punch cards to control commands. So punch card would look something like this. So Babbage would use punch card to exchange input and output with the machine instead of purely metal gears. And the machine were able to perform more efficiently. The analytical engine was able to solve very complex functions, such as implicit equations, where the dependent variable cannot be easily isolated on one side of the equation, such as this one, x squared plus y squared equals 1. During the development of the analytical engine, Lovelace pointed out that the analytical engine could do more operations than any other calculating machines before. It could achieve conditional branching and looping, which is commonly used in our modern computers. She foresaw the immense future of the machine and almost magically predicted that the machine, like analytical engine, would be able to store and even create pictures, music, words, or any other informations. Lovelace also presented an algorithm to generate the Biruni numbers, which looks like this. It is a complicated series with no patterns on the analytical engine. And this was considered the first computer program ever written in the history. Continuing to the fourth stage of computing machines was the Turing machine. Alan Turing was considered by many the father of modern computer science. So in 1936, during World War II, Turing invented the Bomba machine. The machine was the first electromechanical machine with switches, and it successfully deciphered Nazis' code, as shown on the picture here. That was really impossible for humans to calculate manually. So the code would go into the machine, and the machine would be able to decipher what the code was trying to say. Turing also brought out the idea of a Turing test, a theoretical question used to test if a machine is intelligent. Turing presented the question whether a machine could think, whether a machine could be considered as intelligent, just like a human. And his answer to this question was that if a human cannot distinguish a machine from a human after talking to it, the machine should be considered intelligent, just like a human. And in 1939, John Atnes and Clifford Berry discovered the benefits of binary system. It is an efficient computer calculating system, and it is faster and more efficient than the decimal system used before. So electronic circuits could represent two states, the on states and off states. And in binary system, with its digit of 0 and 1, it worked perfectly with it. So for example, to store a number like 128, which is one followed by 7 zeros in binary, it would take 30 switches to represent this number in decimal, because each digits we would need 10 switches, so it's 30 switches. However, in binary, because we have the on-off states, we only need 8 switches to represent this number, to store this number. So from 30 switches to 8 switches, it is a lot more efficient and just faster for the computer to process. And after this binary system, digital computers were forming and building up slowly. So finally, this is the fifth stage of computing machines. In 1946, John Mauchly and John Arctic built the ENIAC, electronic numeral integrator and computer. It was the first electronic computer. So data was inputted into the machine from punch cards, which made the calculation powerful and fast. And both ENIAC storage and calculation use vacuum tubes, making ENIAC capable of performing sophisticated engineering problems at electronic speeds. And ENIAC also had a programmable environment. By simply plugging in some additional computing parts stored with various settings, the machine were able to calculate anything instead of one equation like other calculating machines. There were also many developments in computer science, and the internet was a good example. So we all know about internet and we use them every day, but few people really know the history behind this great invention. So in 1969, Leonard Klingrock successfully sent messages between two computers, and an advanced research project agency network, the first internet, was set up, and it was used by American military department. And networks become super useful for people to communicate in private safely, and it was slowly commercialized in the 1990s and was renamed the internet. And moving on to artificial intelligence. So when the term AI is introduced, we would most likely to think about a human-like robot, like the 3CPO in Star Wars. But however, there is a difference between a weak AI and a strong AI. So a weak AI is AI that only perform one single specific task, such as like a search engine. The user would give it a search term, and it would return the search result back, some websites or images. It can only perform one single task, whereas a strong AI should be able to perform many functions and even eventually teach itself how to learn. A strong AI would be like an example in what we see in a regular science fiction. But however, in today's world, most AI, actually all AIs, are weak AIs because strong AI is not yet to be made yet. And today I am going to most focus on the weak AI. So the first machine, the Deep Blue, was invented in 1997 by IBM, and it was a chess playing machine. It was developed to predict the best movements on a chessboard on the winning rate, and it creates predictions by playing many games repeatedly with itself and constantly improving. It also beat the world chess champion, Gary Kasparov. In short, Deep Blue taught itself to become a chess grandmaster. And natural language processing is a branch in artificial intelligence that deals with the interaction between computers and humans using human languages. So basically, AI uses NLP to talk to humans. For example, in Google Translate, it first converts language A, the input languages, to the keywords in NLP, and then using the NLP, convert it to the desired language, allowing people to speak different languages and to communicate directly with each other without learning each other's languages. The second significant technology is deep learning. The definition of deep learning is a branch in AI that could learn unsupervised. So in the example of Google Spring's photo recognition technology, the team imitated the brain nerve cell in a human brain by creating a complex network in code, look like this. And so the program learned to tell if an image is a cat by recognizing patterns like tails, whiskers, and pointed ears. And the final accuracy of correctly recognizing pictures of cats was over 75%. So the team would give the AI some input, which also known as features, and the AI would teach itself how to manipulate the hidden layers and finally predict the output. Even with all those amazing technologies we have today, there are still many questions that could not be solved simply because of the complexity of the calculations. And this is why quantum computing was introduced. So quantum computing runs under the law of quantum phenomena. So a classical computer run under the binary system. So the answer is either a 1 or a 0. However, quantum computers give answers in a range of possibility from 0 to 1, like this image here. All the information stored in a classical computer would be either on the 0 side, which is like a 0, and or a 1. But quantum computers are able to calculate with any point on this spectrum. It is more like a possibility of range. So with this very new feature, quantum computers are able to achieve incredible speeds that makes the impossible questions possible to solve. It has immense values in medicine, optimization, and AI technology. And this is the latest technology in the field, and it is not reliable enough because of the very nature of quantum computing. But scientists are working on this technology right now to improve it and making it more reliable. And this is all I have for today. Thank you very much.
Emerald, thank you very much for your presentation. That was wonderful. It was great. The whole history that you went through all the way to modern times. Let's see, if anyone has any questions, again, as a reminder, if you look at the lower bar of your Google Meet, you'll be able to select the icon of a raised hand, and you'll be able to answer some questions. So let's take a look here. Well, the first question I have is from Ms. Curry.
Emerald, that was a great presentation, and I actually learned a lot. I had known about some of the early stuff, being a history person, but not the more recent. I have a question about the recent AI work that's been done. You mostly focused on the weak AI, but strong AI is coming, I'm sure. And my question is do we have anything to be afraid of as human beings with the development of strong AI? Like so many science fiction stories and movies, have the robots taking over. Do you think that that's a possibility at some point from what you've researched?
Yeah, thank you, Ms. Curry. That is a great question. Yes. So this question is definitely considered by many. And during my research, there were many books that discuss this question. So the answer to this question is no. So basically, we right now have no technology of developing a true strong AI, and it is like really, really far from actually developing one. And even if we have a strong AI, there is a difference between if a AI could do the calculation correctly or do the task correctly, than actually understanding why is he doing the task or how to do this task. It's imagine this is an example I read from a book. Like, it's if someone let's say if Miss Curry, you go into a Chinese classroom and you could be there, like can't understand a word of professor's like message on the board, but if I pass you a note saying that whatever your response was correct or incorrect, then you are like you would slowly, maybe let's say it's a math class and the answer is always 1, and then you would slowly like understand that no matter what's on the board, you are just going to write 1. So you don't really understand. The AI could not really understand the question, or like maybe say like don't really know why is he doing the problem or how to solve all the problems, but he would be able to solve the questions correctly. I guess the concerns here is that even if AI becomes so powerful that it can do so many things that humans cannot, it will never really have a free will or have his own thoughts.
That makes me feel so much better, Emerald. Thank you.
Okay, so the next question is going to come from Devin.
Hi, Emerald. Great presentation. I just have a 2-part question. So with deep learning, why can't the programmers see what's happening in the inner layers or the hidden layers? And then how do we know that an AI gets its prediction if we don't know its thought process?
Okay, this is a good question. So the hidden layers indeed cannot easily be visible to anyone, or at least it's like it doesn't really make much sense. So programmers could use commands to output all the nodes, which is the data in between the input and output. But so like each in the hidden layers, there could be hundreds of layers of nodes, and each layer could have hundreds of dimensions. By dimensions, I mean like variables. So we as humans have a hard time even imagine like a 4-dimension data. So data in 100 dimensions couldn't really be easily visualized or understood. And this is why like it's called a hidden layer. So the only thing we could look at is if the prediction, the output of the AI are accurate. So after a large number of data sets and tests, which could be like a million or billions of paired data of inputs and output, if the predictions match the correct answer, which are provided by human, the trained AI would be a reliable model for predicting this very specific case. So we could never really see how the AI come up with the model. It is kind of purely AI trying everything out and finding the correct one. But indeed, the AI could solve the question.
Okay, our next question comes from Claire.
Great job, Emerald. I thought your presentation was fascinating. I wanted to ask a question about, did you do any, find anything in your research with the intersection of AI and genetics at all?
AI and genetics. I'm very sure there is. So there is, I think a field called neural computing, something like that. It is definitely a very, very new field that we are still not sure how to develop, because with the current technology we have, there are still so many things like just our biological bodies that we don't know. So I guess we could potentially in the future, maybe in the 100 years, we could understand more of our bodies and our genes and how our brain function, and then we could potentially use it with the AI and other computing technology, and possibly have other things like in the science fiction things.
Okay, so I'm going to follow up with that question, Emerald, because of the complexity of neuroscience and so on. How's that work with a binary system, which is a system I like because it's either yes or no, and the quantum system, which honestly I'm a little confused about because it's so theoretical. Could you explain how the how the quantum system works?
Okay, good question. Like, so like it's actually like really hard to define by only one, like in today's meeting. So like in short, a quantum computer system use a binary system, but how it's used is different. So a classical binary system, as you said, is only like zeros and ones, but quantum computers are different because they use numbers in a quantum state, which can be any number from 0 to 1. It's more of a possibility than a definite number. And so like in quantum computing, it use a qubit as the simplest storing unit, and calculations were made with lots of qubits, and each qubit would have infinite possibility of states. I do believe, I didn't really look into the math behind this because it's really complicated, but I think it uses lots of matrix and really advanced mathematics to calculate the calculations.
Okay, let's see. Our next question will come from Brooke.
Yeah, awesome job, Emerald. I love all this AI stuff. It's so interesting. But in the Turing test, how would like the person talking to the machine, how would that really work? Would it be like a physical machine, or are they just kind of like talking to a computer, or how would that work?
Right. So to first answer this question, the machine doesn't have to have a physical body or talk to the human verbally. So like in Turing's original theoretical example, the machine communicated to the person through text on a screen. So the person was sitting in front of a computer and asked the computer to write a poem, and to make a calculation. And the machine, like the screen, would be connected to another computer, which the tester is not sure if that's like a machine or a human. And in the example, the computer made a funny joke and in the poem and made a mistake in the calculation. So like in the example, like the humor and the mistake in math made the machine look like a real person and deceive the human tester. So I guess like it would be nice to have if a intelligent machine could mimic humans in all ways, including like verbal ability and facial expressions. But I guess Turing's point was that to purely define intelligence, and his belief was that if a machine could talk to a human, then the machine is intelligent. Hopefully that
Okay.
answered your question.
All right. Are there any other questions from the audience? Okay, seeing that there are no questions, I just want to give you a reminder. In the next few days, we will be posting all of the 5 presentations online, so you have access to those. And once the final papers are due, once the final papers are sent in and completed, those will also be uploaded in case you're interested in looking at more detailed research. Thank you all for attending our capstone presentations, and you have a good afternoon, or good morning, rather. Bye-bye.
Bye. Good job.
Bye.